In this problem, we have a 6.4 millimeter diameter cylindrical rod fabricated from a 2014 T6 aluminum alloy, which is subjected to reversed axial tension compression cycling load along its axis. If the maximum tensile and compressive loads are positive 5,340 Newton and negative 5,340 Newton, respectively, determine its fatigue life. And we can use the animated SN figure from YD+. So based on this problem, we can review two important points about fatigue failure. First is this problem given us the information that this is a reversed stress cycle. But if this information is not given directly, we should also tell from the magnitude of the maximum tensile and compressive loads, or from the maximum and minimum loads. So we have two types of stress cycles. One is reversed, one is repeated. For the reversed cycle, the sigma mean, which is the sum or the average of the max and mean, equals to 0. So if the mean stress is 0, then this cycle is reversed cycle. And repeated is when the mean is not 0. That means the maximum mean is not symmetrical about the 0 stress level, then this cycle will be repeated cycle. It's no longer reversed. Okay, so if the information of reverse is not given, this is how we tell the cycle if the cycle is reversed or repeated. Another point we need to reveal is what kind of load is applied to the rod. It's said that this is the axial tension compression cycling load, and the magnitudes of the loads are given. So on the SN figure, we have the stress amplitude. So its stress is not load. So we have to calculate the stress from load. Or from load, we can calculate the stress, and then we use the SN figure. So which equation should we use to calculate the stress from the load? Well, there are two different cases. The first one is, given this problem, is the axial tension compression cyclical loading. So in this case, the sigma max, since we're given with the maximum loads, so the maximum stress equals to load over the cross-sectional area. So that's the sigma max. And also sigma mean will be a negative value. Okay. Another type of load is from the rotating bending test. If the load is from rotating the bending test, then the sigma max equals to 16 F times L divided by pi d cubed. So where the F is the applied load and L is the distance between the supports and the load, and pi d is the original cross diameter of the rod. So please check this equation from the PowerPoint lectures. And again, based on the load type, we choose different formulas to get the stress from the load. Next, let's take a look at the animated graph, figure 8.21, to get familiar with the SN curve for different materials. And one thing we need to realize is the vertical axis, in this case, is the maximum stress, is not the stress amplitude. So it's a plot of the maximum stress versus cycles to failure. So to find the fatigue life, which is the cycles to failure, number n, for a given material, we need to get the maximum stress applied to the material. Also keep in mind that you may be given an SN curve, which is a plot of the stress amplitude versus the cycles to failure. So when you have this SN curve, do check the vertical axis to make sure what kind of stress is given. It might be maximum stress, like in this case, or it might be the stress amplitude. So the first step is to find the sigma max, and then we're going to use the SN figure to find the corresponding N. So sigma max, we already figured out, will be the F max over the cross-sectional area, and which is F over pi times R squared. And it's 4 times F over pi d squared, and we can now plug the numbers in. Remember to convert the diameter from millimeter to meter, and this is 166 times 10 to the 6 Pascal, which is 166 megapascal. And now with this number, we can use the figure 8.21 to find the corresponding fatigue life. Now refer to this SN curve. We move this horizontal bar up to 166 megapascal. The number will show on the top. Let me just move a little bit so you can see it. Just move your bar all the way to 166 megapascal, and then move the vertical bar to the intersection of the horizontal line and the material line, which is the dark red line here, and this point. The corresponding N is the fatigue life. Okay, and the N now is 1.6 times 10 to the 7. And we can write down the result. Refer to the SN curve for aluminum 2014 T6 at sigma max of 166 megapascal. The fatigue life is 1.6 times 10 to the 7. We have 3 identical fatigue specimens, A, B, and C, are fabricated from a non-ferrous alloy, and each is subjected to one of the maximum and minimum stress cycles listed below. The frequency is the same for all 3 tests. Rank the fatigue lives of these 3 specimens from the longest to shortest using a schematic SN plot, where we should use stress amplitude for the vertical axis. We know that on the SN plot, if the S is the stress amplitude, that means the stress amplitude or the cycles to failure will change with stress amplitude. So with decreasing stress amplitude, the cycles to failure will increase. So this is the trend of this curve. But also keep in mind that there's another factor that will change the fatigue lifetime, which is the mean stress. The SN plot is affected by the mean stress in the way that increasing the mean stress level leads to a decrease in fatigue life. So therefore, to rank the lifetimes of these 3 specimens, we need to first find or calculate the stress amplitude. S equals to the stress amplitude, and second, we need to calculate the mean stress applied to each specimen, and then we can rank the lifetime of the specimen. The stress amplitude is the max minus mean over 2, and the mean stress is max plus mean over 2. So now let's make a table to rank the A, B, and C specimen, or do the calculation first. This is the amplitude and this is the mean using the formula we just write down. So now based on our calculation, the sample A and B has the same stress amplitude, which is 300 megapascal, while the sample C has the highest stress amplitude, which is 350. And for the mean stress, there are two different values. One is for A and B, they have the same mean stress, which is 150, and for C, there's the mean stress is 0. So we have two different mean stress values, and we mentioned that mean stress will change the position or the location of this SN curve. Apparently, we will have two SN curves, and the bigger the mean stress value, the lower the SN curve located on the plot. So if I have two curves, that means the bottom one will be a bigger mean stress value. So let's say this is 150 megapascal of mean stress, and with a mean stress of 0, it will be above the curve for mean stress of 150 megapascal. All right, that means for sample or specimen A and B, we need to refer to the bottom line, sample A and B, because this one is when the mean stress is 150. And for specimen C, we need to refer to the top curve, because that one refers to the mean stress of 0 megapascal. And next, we need to read the lifetime or the cycles to failure number n using the corresponding stress amplitude. So for sample A and B, it has the same stress amplitude. Well, let's just check sample A and B now. Now let's make a table to list the corresponding stress amplitude and the mean stress for the three specimens. So using the given data and the formula we just figured out, here are the values for the stress amplitude and the mean stresses. For sample A and B, it has the same stress amplitude, which is 300 megapascal, and sample C has the highest stress amplitude, which is 350. And for the mean stresses, we also have one identical stress mean stress, which is for stress or specimen A and C. It has the same mean stress, which is 150, while for sample B, the mean stress is 0. So we mentioned that the mean stress will change the location of the SN plot. The bigger the mean stress value, the lower the SN curve is located on the plot. So since we have two mean stress values, that means it will move. We will need to have two SN plots. Okay, and one is on the top, one is on the bottom. So based on the effect of the mean stress, this one on the top means the mean stress value is a smaller value. In this case, it will be 0. And on the bottom, it corresponds to a larger mean stress value, which is the 150 megapascal value. Okay, and now we are ready to locate the cycles to failure, the n values for each sample. Before that, let's label the curves to remind ourselves which curve should we use for each specimen. For A and C, we need to refer to the curve that has the mean stress value of 150 megapascal. So the bottom curve is the one we should refer to for sample A or C. And the top one, we need to use the top one for sample or specimen B. So next we have, now we can read the n values based on the amplitude, which is the vertical axis. So for the amplitude, we have two different levels. The first level is the 300 and the second level is 350. So I'm gonna add the two values on the y-axis now. So this one, let's say this is 550. So we don't need to do any calculation, or doesn't need to be very accurate about the scale, because it's just a qualitative comparison, not a quantitative. Okay, all right. For sample A and B, the stress amplitude is the same, so I'm going to draw this line right here. All right, for sample A, the lifetime is read off from this intersection, right? The stress amplitude is 300 megapascal and the mean stress level is 150. So this corresponding n value is the fatigue life of the A specimen. And at the same time, we can read the B over here with the stress amplitude of 300 megapascal and the mean stress value of 0. This is the NB. And now for NC, we use the same way, but now the stress amplitude is 350, is above the 300, and mean stress value is 150. And we use the bottom curve for the C sample or sample C, and this is NC. And now we can rank the fatigue lifetimes for the three specimens. From the longest to shortest, we have NB is greater than NA is greater than NC.